Hi everybody, I'm TzuWei an undergraduate student at University of Florida Indian River Research and Education Center. I'm happy to talk about our project of using sensors to inform and control irrigation research and management. Today we will focus on soil moisture-based irrigation control. We will discuss the Internet of Things application in agriculture, the development process of our system, and the results we got. First, let's talk about technology innovation in smart farming. Farming has seen a number of technological transformation in the last decades. Those high-tech farming technique has allowed farmers to gain better control on growing crop, making it more predictable and improving its efficiency. Smart agriculture is mostly used to denote the application of Internet of Things solution in agriculture. So what is Internet of Things? Internet of Things basically means that Internet controlling things. IoT devices are smart devices that can transfer data over a network. In IoT-based smart farming, a system is built for monitoring the crop field with the help of sensors and automating the irrigation system. These sensors, along with the connection, allow us to automatically collect information from the environment remotely in real time, which in turn allow us to make more intelligent decisions. IoT-based smart farming is highly efficient when compared with a conventional approach, but smart agriculture IoT are not as popular as consumer connecting devices. Yet the market is still very dynamic. The United Nations projects that the world population will reach 9.7 billion by 2050, causing global agricultural production to rise at least 60%. Amongst the challenges like extreme weather conditions, climate change, environmental impact, IoT is helping us to handle the challenge and meet the demands for more food. Not only do IoT-based systems with soil moisture sensors help producers have greater production capabilities, save water and energy, this approach makes farming greener, but also significantly reduce the use of pesticides and fertilizer. The problem with the traditional approach of utilizing sensor technology was that we were not able to get the live data from the sensors. With the introduction of industrial IoT in agriculture, far more advanced sensors are being utilized. SDI-12 is a standard communication protocol that transfers measurements taken by an intelligent sensor to a data logger. An intelligent sensor is a microprocessor-based sensor like a little computer, typically make computation based on the raw sensor reading and output the measured data in engineering unit by itself. Some SDI-12 sensors have the ability to measure more than one values from the soil, and through SDI-12 communications, more than one SDI-12 sensors can be connected to a data logger. However, the commercial data loggers designed for SDI-12 sensors are usually expensive and proprietary. To make smart farming more publicly accessible, a low-cost open-source device like Raspberry Pi or Arduino can potentially be developed as a universal feed and cloud connecting data collecting system by computer programming. Open source commonly refers to software that uses an open development process and is licensed to include the source code, which means the source code is freely available to the public and everybody can modify the code. We have been developed the concept of applying low-cost open-source IoT in agricultural field in the past couple of years to increase the public accessibility on smart farming. In 2016 and 18 workshop, we were using Arduino to build a smart data collecting and irrigation control system with analog sensors. This year, we expand the system from Arduino to Raspberry Pi that the system remains in low cost but higher the performance that allow us to work with more intelligent sensors. Now I'm going to talk about our new system. The data logger we designed is using Raspberry Pi and a commercial SDI-12 and analog adapter that connect with one commercial analog sensor and two SDI-12 digital sensors to collect the volumetric water content of the soil, with different soil-specific calibration equations that are supplied by the factories. Raspberry Pi is a low-cost credit-card-sized high-performance computer that generally costs around $35 in all models. It provides open source systems, software, and general purpose input and output pins that allow you to control electronic components for physical computing. The data logger itself only needs a 5-volt power supply to power on, and the data logger outputs an internal 5-volt battery to power the sensors. However, some of the sensors might require more than 5 volts to be powered, like the acclimatity soil moisture sensors require the supply voltage range of 6 to 15 VDC. Then the users will have to wire an external power supplies to operate the system. In our case, we use a 12-volt rechargeable battery to jump wire the acclimatity sensor and use a 12-volt to 5-volt converter to supply the data logger and the rest of the sensors. We also wire a solar panel as a backup supply that allows the battery to be charged constantly. The computer programming language we use to develop the system is Python 3. Python is an open source, simple programming language that is already installed in the Raspberry Pi. I started to learn how to program the Raspberry Pi with Python since December last year, with no computer science background. The beauty of the open source language is that it is free to use, and you can learn everything you need for the project from the internet. I'm sharing my learning resource here so that everybody can learn how to develop their own smart farming system. If you scan the QR code to the right, it will lead you to the links. Here's the code example we wrote to develop the system. First, the code is to let users to input the information they want for their data logger. When you write an input function in your script, the user can input an answer of the sentence you write inside of the input function. Then program will run the code to identify the sensors and print out the sensor info. After that, it will start the sensor measurement and request data in response to the measurement. In our case, the Decacon GS3 sensor measures the electric permittivity, temperature in Celsius, and electrical conductivity. The acclimatity sensors measure the same measurement the GS3 sensor does in addition of volumetric water content. And the ASHS measures the voltage reading from the 10HS analog sensor. After telling the sensors to measure the soil condition and retrieve the sensor reading back to the device, we program the device to send those data to the cloud through the internet that allows users to monitor the field remotely in real time and save the data to a cloud and local SD card for further analysis. The cloud server we use to real-time monitoring is ThinkSpeak, which is an open source IoT analytic platform service that allows users to aggregate, visualize, and analyze live data stream in the cloud. Every user will have their own channel ID and API key that are provided from the ThinkSpeak website after the users create an account. To let the sensor readings live stream on the channel you create, simply replace this part of the code to your own channel ID and the API key, then the system will send out the data accordingly. They also provide a free app you can download to monitor the data through your mobile device. Not only the system can collect and analyze the soil moisture data in real time, we program the Raspberry Pi to control the irrigation automatically based on the sensor readings as well. We control the relay through the Raspberry Pi's GPIO pin to turn the sonar valve on and off, which that control the watering systems. Relays are switches that open and close circuits electronically. And sonar valve function involves either opening or closing an orifice in a valve body, which either allows or prevents flow through the valve. We program the relay to be controlled based on the 3 sensor readings of the volumetric water content. If the VWC values of the 3 sensors are lower than 20%, Raspberry Pi will output 5 volts to the relay to turn the relay on for 10 seconds and turn it off. When the relay is on, it will trigger the connecting sonar valve to open and let the water flow through the pipe to the sprinkler. At the same time, the system will also update its irrigation status to the live stream platform. Here's the result we got. The electric permittivity is the ability of a substance to hold an electrical charge. The value of the electric constant in air is 1 and in water is 80. We test how accurate the sensor readings respond in water and in air, and the data logger we designed successfully record the sensor readings. The dielectric permittivity reading in water for ASHS 103 sensor is 76.0, ASHS 2 TDT sensor is 73.3, and ASHS Z THS analog sensor is 81.4, and in air is 1.42, 1, and 2.34. Since the analog sensor only reads the raw value, which is in voltage, we apply the calibration providing from the 10HS sensor's factory to get the dielectric permittivity. This was already programmed so that the data logger could calculate the value by itself. We can get the volumetric water content of the soils by using the factory calibration and the dielectric readings of the soil sensors as well. Volumetric water content is the numerical measure of soil moisture, which is the ratio of water volumes to soil volumes. The Acclima TDT sensor doesn't require the calibration because the sensor has already output the VWC by itself. These calibrations were again already programmed in our data logger system. In water, GS3 sensor's reading is about 90%, TDT sensor is 89%, and 10HS analog sensors is 65%. Typically, the range of the VWC is from 0 to 100%. However, the defined range of the VWC for 10HS analog sensor is from 0 to 69%. The VWC reading of the sensors in air all result in 0. The negative values can round up to 0 because there is no negative water volume in soils. We have done several testing from March to June in both sandy and potting soils, and all the data were successfully uploaded to the cloud that allows us to monitor the soil status remotely through the laptop. Here's the QR code you can scan, which will link you to our ThinkSpeak channel. We also analyze the data from the local file and create detailed graphic chart. The peaks of the chart were when the irrigation started. In this page, the QR code you scan will link you to see the example of the file that is saved to the SD card. The GS3 and TDT sensors allows measure the soil temperature in Celsius and the electrical conductivity to read the soil concentration in soil water. We set the system in waterproof hard case and have tested outdoors since March this year. So far, the system has experienced Florida's weather without maintenance requirement. The only issue has occurred was the overheating of the Raspberry Pi due to being outdoor under the sunlight could cause the power consumption went up. However, this issue can be solved easily if the user set the system indoor or under the shed, or using outlet instead of rechargeable battery as the main power supply. The entire system without sensors costs under $200 and it is completely customized. Everything you need to assemble the system is available to buy on the internet. The Python script works on both Raspberry Pi 3 and 4 models and has low limitation on sensors proprietary issue. With this system, everybody can easily have a smart farming system for their own farm, greenhouse, or garden. I want to express my special thanks to UF Institute of Food and Agricultural Science, USDA Citrus Disease Research and Extension, my supervisor, Dr. Rhuanito Ferrarezi, assistant professor of UF Citrus Horticulture Department for supporting this project, and Dr. John Liu, the designer of the SDI-12 USB adapter for technical issues. Attached are the links of the items we used to build the system and the complete version of the Python script you can download if you scan the QR code. You will get access to those links. Thank you for listening, and we are happy to answer any question related to this project.